to this roundtable about the second quantum revolution starts now. We have a very high-level panelist. So I will introduce Pascal Sénélart. Hello, Pascal. You have a microphone. So you're CNRS senior researcher at the Center of Nanoscience and Nanotechnology, specialist in quantum photonics.
Yes.
And you are within University Paris-Saclay. You coordinate education, research and innovation in the wide field of quantum science and technology. You are also co-founder of the startup company Quandela?
Yes, exactly.
That's correct?
Yeah.
So thank you to be with us.
Thank you.
With us too, and thank you to be with us. Albert Fer, so you're professor at Paris-Saclay University, scientific director at CNRS Thales unit. You received the 2007 Nobel Prize in Physics for the discovery of giant magnetoresistance and your contribution to the development of spintronics. So thank you to be with us, Albert, and we will start with you in a few moments. Bruno, good afternoon. So Bruno Deruel, CEO of Muquants. Perhaps a few words about Muquants?
Muquants is a startup company who specialized in high precision measurements based on quantum technologies. So I really believe that we are today the first and still today the only company that can commercialize commercial solutions based on operational utilization of quantum technology. So we typically use laser-cooled atoms down to a temperature of 1 microkelvin in order to perform very high precision measurements, inertial measurements, and time efficacy measurements, basically.
Okay, and before you arrived at Muquants in 2010, and before you were working for the French Ministry of Defense as well as advanced research and innovation.
Yeah, exactly. So I used to work at the French Ministry of Defense for the development of advanced technology for military applications. I'm very happy to see some of my former colleagues in the assembly here. And so, yeah, in 2009, I had this opportunity to participate to the launch of a very innovative startup in association with two scientists from CNRS. And so I made the decision at that time to leave my position at the DGA in order to create the company.
In 2010, 2011. Thomas Cordas, good afternoon. So thank you to be with us. You're Director Digital Excellence and Science Infrastructure at the Directorate General for Communication Network, so DG Connect. So with you, we are going to talk about European topics.
With a lot of pleasure.
Yes. Thank you to be with us. And Marco Herman, your Chief Technical Officer at Thales. So yes, we will have with you the point of view of an industrial, of your industrial roadmap. So Albert, I will start with you. In a few words, because I don't know if everybody here know a lot about quantum technology. So quantum physics may be perceived obscure to many. Can you tell us what is behind this type of physics?
Okay, so quantum physics is an old science. It has been created at the beginning of the last century, at the beginning to explain, to understand the quantization of the energy level in atoms and the quantization of the emitted light. And so what has been shown merely is that the particle in quantum physics can be described by wave functions with quantized energy, and that these wave functions can, and in addition, a few years later, what has been introduced by the quantum physics is that the particle, there is 2 degrees of freedom. It is not only for a particle a degree of freedom of motion, but also another degree of freedom that has been called spin. Is sort the second degree of freedom is the orientation of a sort of vector, which is a spin, that on a given axis can take either the value 1/2 or -1/2, and all the spin states can be also combinations of linear combination of these 2 spin states. In the same way, wave function can be also, for several particles, can be also a combination of the wave function of all the particles. So this first generation quantum physics, mainly in the second part of the century, led to the understanding, to the clear understanding of the property of matter, metals, semiconductors, and magnetic materials by understanding the property of the matter at the nanoscale, at the scale of the atom and the particles. And this is maybe the first revolution, the clear understanding of the property of matter by applying the quantum physics at this level, the macroscopic property being a sort of average of the property of the matter at the nanoscale. And this led to the application, you know, electronics, optics, communications that we had in the last part of the century. So today, what is there a second revolution now? As it was maybe the first revolution. Yeah, yes, in some sense, yes, because now with the development of technologies, experimental technology, it becomes possible to study not the property, the average property of the macroscopic matter, but also the property of a given small quantum bit particle, say the property of an atom, the property of a single spin in a, what is called a nanodots, and for example, the property of a quantum circuit, superconducting circuit with tunnel junctions. And so it becomes possible to study and manipulate single quantum objects at the atomic scale. And this leads to many applications, to many new property applications that will be discussed by this panel. Okay, so I don't go forward in this direction. What I can say is, in fact, physics is always advancing in several directions. Science is always advancing. And in fact, maybe there are other revolutions that are emerging today. And for example, if you read a scientific paper, you can see also that this expression, quantum state of matter, for something completely different, for a new state of matter that is not described, in which, for example, the electron have not 2 degrees of freedoms as the particle in quantum physics, but only a single degree of freedom. So spin and momentum are what is called, there is a looking between these 2 degrees of freedoms. So this is a new picture of quantum physics. And also this, there is a lot of research now also in this direction, which is not the direction discussed today, but with a lot of application also coming from the, for example, in our lab, we are, so these new materials are called topological materials. And best example is what is called topological insulators. These materials with, in contrast with usual quantum physics with 2 degrees of freedom for the particle, there is a single one. And for example, there are a lot of applications that can be obtained with this new material. For example, we are in our lab, we have a collaboration with the company Intel for the development of a new type of logic and memory components based on topological insulator, on the property of this topological insulator, which are important because with this locking between spin and momentum, there is a very easy conversion between electrical current and magnetic bit, magnetic inscription. And so this is an important part in any computer, memory and processing. And so the project that we have with Intel is to design new type of logic and memory component with, according to the wishes of Intel, will have low power and a very low consumption of energy, and also more adapted with some new architecture of computer, for example, for neuromorphic computing. And so it was, and there are also other directions. So in fact, what I want to say, that there is a second revolution, but in the scientists knows that will be also other revolutions.
A few weeks ago, we've heard that Google said they have a new sort of new technology. What is your point of view about the publication of the Google research?
Google on the quantum computer?
Yes.
Oh, okay. So, yes, it was a demonstration of what can be done with a quantum computer. And they was saying that what has been done, this sort of not total calculation, but a sort of demonstration will be done with digital computer in during after calculation of many years. You are referring to this, okay?
Exactly, yeah.
And then IBM replied that in fact it could do the same job with only 2 days or something like 2 days. And so the problem, okay, so it's true that the demonstration of Google was a formal demonstration of the power of quantum computing, and maybe they exaggerate a little.
Little bit. Okay, thank you. So let's talk with you, Pascal Sénénard. So just to know about the power of academic in Paris, but also in Saclay, but also in France. So the Saclay Plateau Research and Innovation Cluster, where many top leading academic players are located, is strongly engaged in quantum physics and application. Can you tell us the size of this research and some of your main scientific challenge?
Yeah, so I think the first thing to say maybe about this topic about the second quantum revolution is you have understood that it's still very subtle physics that we are discussing. So it's very close to fundamental physics, but the new innovations are ready, many of them are ready to come out of the laboratories. So it's a field where applications are emerging, but there is a strong connection with academics. So the French scientific community has played a very important role in the advent of this second quantum revolution. I mean, we have, of course, here Albert Fert, who is Nobel laureate, but we have other Nobel laureates in France that were at the center of this second quantum revolution. We can just cite, for instance, Serge Haroche. And we have many of the first demonstrations at the international level, which were done by French scientists, which are also very famous, like Alain Aspect, who demonstrated the quantum nature of entanglement, if I want to simplify. And there is a founding father of this field as well. First demonstration of quantum communication, first fabrication of this tiny circuit that is cooled down to very low temperature to do a quantum computer, development of new quantum matter, etc., etc. First demonstration of the use of a very tiny impurity in diamond to make new sensing application, and the list goes on and on and on, etc. So, and the science in France, the influence on the French scientific community in this domain is clear. If you look at if you make a list, or I've done it for my institute, the Center for Quantum Science and Technology in Paris-Saclay, if you make a list of all the collaborations that these researchers have, it's just impressive how influential they are at the international level, everywhere. So we are a very strong scientific community. And if I want to just give a better taste of what all this entails, quantum devices that are emerging are based on different physical platforms, and we have several of them around this round table here. So cold atoms that are trapped at very low temperature, spins, physics with spin junction and new material. I myself use semiconductor devices and photons. And there are many others. I cannot list them, but there are many of them. And France is everywhere at the very best level. So that's very clear. The other thing that I think we should say is that there is also a lot of potential in terms of transfer in the laboratories. And there are the first quantum startup slightly emerging. So Muquans is, of course, one of the precursors in France. But there are others, especially at Paris-Saclay. There was two startups created in the last 2 years. One with quantum computer, which is based on cold atom, which is called Pascal, not me, but with a Q, Pascal. And my startup, which we created with Nicolo Somaschi and Valérie Angès, who is commercializing a building block for optical quantum technologies.
And in an European point of view, we are in the top leadership between Germany,
So
UK?
my perception of this is that I think at the scientific level we are very high at the European level. In terms of transfer, we are not so good. I mean, we are very few startups starting to emerge from France, but we are working on it. So it's one of the things that we have started to initiate in the last few years to encourage the community to those researchers who are, in general, when they've chosen to do quantum physics, true believer of fundamental physics, and it's harder for them to get interested in industrial transfer. But now it's coming, and I would say that there is a new generation of quantum physicist researchers, and also in quantum computing in terms of software, for instance, who are ready to enter the game at the innovation and startup level and collaborating with many industrial now.
Yes, you have some strong relationship with industrial. Like,
exactly. So this is the third part, maybe, of this story, is that in clusters like we have in Paris-Saclay, it's not only education research, but it's also a lot of collaboration with industry at different levels. Some of them want guidance, some of them want that we help them supervise our PhD students, and with some of them, like for instance Thales or Atos or even EDF, we have joint PhD or joint projects and even joint laboratories.
Is the quantum technology, is this technology, you need a lot of money, you need a lot of
it's deep
financing,
tech, right? I mean, on the hardware side, it's deep tech. I mean, everything we are discussing here is really very demanding development, and if you want to end up having application, and this is one of the things that we also have in Paris-Saclay, you need to start thinking on how to integrate, make things compact, reliable, reproducible. So yes, it's a field that needs a lot of money if you want to have something really emerging fast.
So thank you, Pascal. Marco, for the industrial perspective, Thales is very interested by this technology. Can you tell us more why you are interested in this technology and what kind of application are you targeting today?
Yeah, sure. We are indeed interested, actually. We are working on that for 30 years, a part of this work in common with our academia partners, as Pascal rightly mentioned. The reason of interest is that we believe it will have a high impact on the group, and why it will have an impact. Let me just summarize what the group is. The group is Thales is a group that actually helped the customer to make the right decision at the right moment, which implies that beyond this function, there is actually kind of a decision chain where the customer will need to capture data from the environment, from the situation. It will need to transfer data to another place, to process them, and then make a decision. Two of these 4 steps, sensors and communication, will be completely revolutionized by the second quantum revolution. And we have proofs in the labs already. Academic labs have their proof as well. The change is not that it will improve by 10% or a factor of 2. It is changing by 100, 1,000, 10,000. So when something is changing by orders of magnitude, the life is different afterwards, to the extent that not everybody can even imagine how different it is. But given the fact that 1/3 of our activities is on sensor or related issue system with the sensor, what is sure is that it will be impacted. So, and the reason why we are so excited today on that is not because so many people are starting to talk about that, but because we have, as I said, prototypes in the lab that demonstrate the feasibility of that, because the science has leave the purely scientific debate, and we have experimental proof. For one of the sensor, we did a field trial with the customer, so we are really very excited on that. You know, whatever sensor you look, or sorry, yeah.
Who are your customers, for example?
Well, we are mainly looking on the customer in our verticals. I mean, all verticals we are working in, being space observation, being defense, of course, being also air transport or train transport, they need kind of sensor, navigation system, which is a center of methodology too. So they will be all transformed. But I think the point is that when you increase the sensor by such a large magnitude, other applications will appear that are not today in the main verticals of the group, by geology, health. I mean, you know, the magnetic resonance is already a kind of daughter of quantum physics, which is still using a kind of macroscopic interaction with the biology. If you could that at the cellular level or protein. I mean, the story of biology, health is changing completely. So I think that the rationale for doing that, yes, we have a very strong one, Thales one, but it goes much beyond the Thales. And with few examples that Albert Ferrer recalled on what is the impact of the first so-called third revolution, actually changed the world. I think that very probably the second one will change the world also, not only Thales. But we would like to be, at least in our verticals, pioneer of this technology.
So let's talk about you, with you, Bruno. Muquans is already a very successful company, as Pascal said. How do you see the future, expanding your portfolio, maybe an international company? Do you fear competition?
Yeah, of course, I think it would be a major mistake to underestimate our competitors. From a general point of view, we can see that everywhere in the world, quantum technologies are extremely fashionable. We see plenty of extremely bright scientists and product managers that are very excited by the market opportunities that are raised in various fields of applications. They are extremely motivated. They are smart people, and they receive massive fundings from both investment funds or their national governments in order to raise and to develop an industrial capability. So this is what we have in front of us. So of course, in our case, Muquans, I think we still have a very interesting...
How many people you are today?
We have 30 people, so that's still a small company, but I think we've been very successful at reaching a first milestone. But the way I see it is that it's only the beginning of Muquans. Okay, we have been mostly working on research and development, developing also our mark, our image, but really we're only starting to develop the product and really to address all the market opportunities that we have in front of us. So that's where we have today. So I still think that we are way ahead compared to many of our competitors. But still, as I said, there are many people, bright ones, very capable ones, with a lot of money, a lot of ideas, a lot of motivations, and of course, they want to be first, like everyone else. So we're still fighting, I think, again, we don't have to rest, and we still need to try to innovate and try to develop our market shares.
And what do you need? What do you need today? Do you need some more customers, more resources, more engineer resources, more money to invest in your technology?
Well, we need to work in different directions. So what we have today is what we have done is really demonstrated our capability to launch, to develop a product for polio that's composed of a first generation solution. So what do we have now? We know that we can build some gravimeters that are interesting for geophysicists, for some applications. We have atomic clocks that are interested for time and frequency measurements. Also, we propose a complete set of laser solutions, and that could be interesting also for quantum computers like Pascal, the company mentioned by Pascal. Okay. So that's what we have now, but we have plenty of improvements to bring to this equipment. We know that, okay, we have some functionalities, we have demonstrated interesting performances and already a first competitive advantage, but we know that quantum technology can do much better compared to what we have now. So we need to work on R&D in order to end up with better products. So in order to make that happen, we have plenty of ideas. So now it's a matter of money. So this is one thing. The second thing is also developing our manufacturing capability in order to ramp up and demonstrate really our capability to build more units in a reduced lead time with lower costs, and that's absolutely necessary if you want to address a bigger market. Okay, usually we feel some pressure from many customers in order to reduce the cost of the solutions. We know it's feasible, but some investments are required in order to make that happen. And then the last direction also we need to develop is also at the commercial level. So we have mostly sold in Europe and in China so far, but our sales in the United States has been extremely limited. So we also need to invest in this direction in order to expand our sales in North America, Canada, and also South America.
And is it to work with large industrial like Thales, or how is your commercial strategy?
Not at this stage. As I said, most of the work that we have done over the last 10 years have been in demonstrating our capability to bring to the marketplace some quantum solutions. Now we know we can do it. We can generate sales. So, but you know, we're still at a stage where our revenues remain small. Okay, well, typically we have generated 3 million euros revenue last year, which is okay for a small company of 30 people. But I mean, today it's still a small business. Okay, of course it's going to develop, but I think that we're only now starting to reach a stage where we can expect an interesting market development, both on the solutions that we can propose for sensors and also maybe in associations with quantum computing companies. So maybe this will happen in the future.
So we have to be ready for the future. So you say it's a small market, but Europe has put a special program, Thomas, flagship program on these topics. Can you tell us more about the scope and the roadmap of this program with your DG Connect?
Maybe before I tell you a little bit more, let me tell you that quantum is an area that was heavily supported by the European level programs almost now since 15 years. More $500 million of investment so far since early 2000. And there was a critical moment, I think around 2017, 2018, where we thought that we have something like 4,000 to 5,000 researchers in Europe to do something bigger. This is the origin of the flagship program that we started in 2017-18 with 130 million euro. I would have loved to have 1 billion, but there was not available at that moment. So we started with 130 million euro, heavily supported by the Dutch presidency at that moment. Would just really like to remind you that at that moment there were very few national programs. And if you want to succeed from a European perspective, first you need to have national excellency and then European excellency. If you don't have those, forget about it. So we need critical mass, we had it. We need to have programs that make our scientists dream about it, and I think now start having it, both at European level and national level, and we need to make sure that the IP we produce stays in Europe. I will come back to that because this is a critical issue that we would need to face in the coming years. So, flagship, yes, so we started 2018. The beauty of the exercise is that we have grouped somehow, managed to group all the member states around this kind of philosophy of launching a large-scale European initiative that is bringing the best of the people together, where our scientists and our researchers have developed a strategic research agenda, which is our technology roadmap in 4 or 5 different areas. I think they have been mentioned here: computing, communication, simulation, sensing, but also we need also to progress in basic science. So these are the main areas where we can find in this technology roadmap and scientific roadmap. And most importantly, the idea is not only to bring the best researchers together, just for looking for the next big round of what the deep science can do, but to create our deep technology perspective of the future. This is the very essence of what we try to do at the European level. And this is the very essence that we will certainly try to do in the years to come. Yes, we need more research on basic science, and we'll continue doing that, but definitely we need much more interaction between our scientists and our industries, be it small companies like Mukons, or be it bigger companies or very big companies like Thales, to make it happen in the near future. And from what you hear here, the near future is basically now and in the next few years. So let's not lose that opportunity. And this is one of the reasons we started, just to open our appetite. Maybe in a few minutes I will come back to that.
Yes, Albert?
Question, what is your feeling after the development of the first flagships?
Yes, first of all, let me say, what is the chance of Europe here when you hear the multi-billion investments of the Chinese or of the Americans? What is our response? I mean, is it a response enough to say that France will put 50 million or 60 million or even 100 million in investing in quantum, or even something similar in Germany or something similar in the Dutch or in the Italian government? I don't think this is enough. I think the only way that we have in Europe is to bring our best people together for facing together the big challenges of the future. So this is exactly what we started doing in the flagship. And this is where we started creating the first instances, just to give you an idea, of what would be the future computing platforms, for example. So we develop now 2 platforms, to use exactly the expression that Pascal has used. one which is based on, I would say, superconductive technology, and one which is based on trapped ions. Is this enough? When you hear the announcements of Google, of IBM, of Rigetti, and some others there, I would say of course, you have to understand that these are commercial companies and they need to make, to convince their stakeholders that they invest well their money. Yeah? So don't forget that. But I would love to do the same from an IP perspective in Europe. Yes, we can do that. And yes, we are doing it. So now we are not yet at 50 qubits, but very soon we will be in 50 qubits, probably by middle 2020. So we are working on that very, very hard. And I'm pretty sure that maybe in a year and a half of now, we will be in position to make at least equal valid announcements, because there is a lot of hype on what they are announcing about what is true and what is not true. But when we will go out there, you can make sure that it will be true. So this is the challenge we have. And the same challenge applies in all the areas. So in quantum communications, we are now on, I would say, having large consortia that are building the quantum repeater. Without a quantum repeater, you know very, very well that the communication cannot fly more than 30, 40 kilometers in terrestrial networks. And without a repeater, you would need to have sort of trusted nodes to be able to repeat the information. For example, when you need to transmit your quantum key distribution keys. So this is, of course, not an acceptable solution anymore. So we have to work on that to make sure that the future is not the internet that we know today, but the quantum internet that we may have in 10, 15 years from now. This is where we are all working together. I'll come back to that in a moment later.
Albert, do you think it's time for Europe to accelerate in this technology? Your microphone.
It's time to jump. In fact, in the fields where Europe has a good position for the research and for the industry, and so is, for example, for quantum technologies. The question is, for example, for electronic components, where now there is some advance by all the countries in Taiwan, China, Japan, US. What is the possibility to catch them?
Thomas, you want to make? Marco, want to give an answer, Marco?
Yeah, I mean, on semiconductor, the silicon one, yeah, I mean, we still have an important company that is ST Microelectronics, where we actually put the strategic issues. But Albert is right in the fact that this roadmap is, in a way, has diminished in terms of investment in Europe, because we are also in the industry where it's very, very much capex intensive. But for me, this is one reason more, and give you a really right to Thomas' comment, the reason more that we don't miss the next one, which in a way, I wanted to comment that one as well, but the quantum technology is actually a new industry to be built. It's not just changing what we have already, but there is a new supply chain to be built. In supply chain where actually company like yours and many other startups will have the role to play. It's not only the quantum chip, it's all the environment, it's the cryostate, it's the material, the crystal for some solutions, so forth. So there is, to some extent, a green field, right? And let's try to develop a kind of longer vision that some of the Asian countries have, and they can forecast. I mean, you know what the 50 years roadmap agenda is. I think we need in Europe to have this long-term view and patiently build it. Because as soon as you stop it once, you never recover. So let's try to engage our forces in the battle we can win.
Okay, so, let's talk about this with Pascal. So the French government is about to issue a report and recommendation of quantum information, technology and application. How do you feel the academia should position itself? What are the next steps?
Yeah, so I hope it's more than a report that we will get. I hope it's a plan with money.
I hope so.
Because we need to move forward and we have many things to do. So you're asking me, I am a CNRS researcher, what is the role of academia in that? I would say there are three things that academia has an important part to play. The first one is Right now, I think it's fair, and then it's a rough number, but I don't think I'm too wrong to say that most of the quantum innovation, as large as probably 90%, are in academic lab right now. I mean, Thales is one of the very few exceptions in terms of companies, apart from startups, where you have quantum devices developed. So it's a lot of beautiful innovations that are still in the labs, and scientists are not engineers who are not building prototypes, etc. So we need to start feeding the chain, and I think many researchers are ready to do that. So this is the first thing they should do. But also, they should not stop investigating very fundamental physics, because we know that there will be the first generation of quantum repeaters. There will be the first generation of quantum computers with a few number of qubits, the first generation of sensors. And we already know that to get to the second version and the third, etc., we will need new leaps in the material development, in the technology, etc. So we need to keep a very fundamental research that is able to provide the next generation of quantum matter, quantum devices, technologies that will continue to feed the system as it grows. The third thing that academics must do, and it's their job, but it's going to change a little bit with this context, is to educate more students, define new tracks between pure fundamental research or pure academic tracks and engineering tracks, and also interdisciplinary training. So we would like at some point that people developing the hardware for the quantum computer or for the quantum repeater also understand a little bit of the protocols that will be used to program them, the quantum algorithm or the quantum protocol, etc. So we need to create new education programs,
I know in academic program you have a lot of sections.
Exactly.
Mechanics section, physics section, mathematics.
Thank you for
section.
making this image here. I mean, in France, we are very good at doing this.
Yes.
Physics, engineering,
and
chemistry.
even for a career, you have to stay in the same...
I am the typical example. I am nowhere. I am in between four sections of this, and nobody knows where I am. And so it's why I'm also very motivated to make these, transverse connections, which I think are just essential for if we want to move faster, more efficient, and smarter. I mean, to be smarter in what we do, because one community, although it's a different system, we exploit the same concept than the other. And an idea developed here may not work, but if I take it and take it to my system, it may make me move forward much faster.
Bruno, is it difficult to start like in the research and then to go in the business to find your business model and to be on all the line from the research to the business?
Well, it's true that you really need to have a really transverse capability, because developing a quantum company, it's all about understanding complex science and transforming this science into a product. So you need to have some competencies in manufacturing, in high technology, in industry. You also need to have marketing competencies because, it's not just a matter of playing with cold atoms and, you need to provide a solution to one customer. And in order to make that happen, you need to have a good feeling and a good market knowledge of what might be interesting in different fields of application. So in the end, in order to be relevant in the strategy that you want to implement, it involves many competencies in very different areas of expertise. And that's why maybe it makes this kind of projects extremely unique, because you really need to mix various competencies. And maybe, one of the things that maybe my background is in this term could be interesting, because so I was graduated from Alain Aspec's group, so I had background in fundamental science, Bose-Einstein condensation, quantum physics, and then I moved to the industry, telecom industry with Corning. I spent a few years with Thales, so we're former colleagues, although you probably don't remember me. Then I moved to the DGA, and I think this background was extremely interesting for me to learn on many different aspects that have been extremely interesting for the development of the Muquans company.
Oh, Pascal, yes.
I realize that I think that I should mention something else about the role of academia. If you want to grow this quantum ecosystem, what I just said, that we will create for students new paths, etc., it's going to take some time.
Yes.
And we cannot wait for us to give you the next generation in the 7 years of quantum engineers. What I think the academia can do as well is to provide training for engineers in companies who wants to get knowledge to what is this quantum physics, etc. So we also can provide this kind of education for companies to help do the transition, at least progressively, towards this quantum technology.
I see the parallelism with artificial intelligence. It's
Probably, yes.
probably the
Very
same
soon.
thing. Thomas, just a few words about the research program Horizon Europe. Will quantum technology be one of the priorities of Europe? With specific additional program?
Yes, maybe before I reply to that, let me tell you that we are in a transition period and many new things will happen. So since 2 days ago, we have a new commission. And by the way, the new commissioner is French as far as the digital, the defense and space is concerned. Somebody who is coming from an industry sector and who knows digital perfectly well, and a big supporter of quantum.
Yes, I think
Second,
you're talking about Thierry Breton, if nobody...
Yes, but officially he will be in office Monday.
No, exactly.
So second, the new president, so Ursula von der Leyen, announced digital as one of the big priorities for the future, and quantum being one of the key technologies that we will support. And it's not the only one, because one big part of the political agenda is digital sovereignty, technological autonomy. These are perfectly, areas, quantum, high-performance computing, artificial intelligence, nano-microelectronics, microprocessing technologies, cognition, robotics, etc., where Europe, the only future for Europe is to innovate. There is no other future. Either we innovate or we depend on the others, and there is no future. And you know how the geopolitical perspectives are today. Tomorrow, the US may tell us, for different reasons, embargo on basic technologies. So forget about many of the areas we are doing. And some of those are directly of concern to what we are doing here, including equipment, including micro and nano aspects, etc. So that's why we will be massively investing in the next few years. I think the new commission and Mr. Breton in particular will announce our, I would say, ambitions for the future. And it's not just ambitions. It's because we all feel that we have the capabilities in Europe, both the research capabilities and the industrial capabilities, to making it happen. And therefore, I would rather like to be optimistic for as far as the future is concerned. Now, in quantum in particular, I said we are just opening the appetite in terms of quantum, since we are now in plain reflection mode about what would be our big strategy for quantum in the future. You can guess that it's going to be structured around 4 major pillars. One is continuing our research flagship, fundamental for the future, in a few areas where we have assets to do. I mentioned some of those. The second one is we don't need to wait for 5-10 years to have this technology deployed out there. So there are areas where we can already do it, and we have announced at least one, which is the area of quantum communications infrastructure. There is a white paper that I understand where Thales is co-writer of that. Yesterday, there was an interministerial meeting in Sevilla where the ESA was having part of the budget for realizing our ambitions in terms of deploying a pan-European quantum infrastructure for ensuring our communications in the public sector, and not only. So we are building that, and this is a plan for tomorrow. It's not a plan for the next 10 years. So the investments, I don't know yet, but I would certainly bet that this is of the order of a few billions. Why is this important? Not only because we will therefore deploy quantum technology, but when deploying a quantum technology, we'll certainly make investments in the kinds of investments that we need to have for building components, electronic components, photonic components, single photon detectors, photon transmitters, whatsoever, quantum random number generators, etc., that we need for making this happen. This is the importance. And we want to do it digital autonomy. Sovereignty means the possibility to do it with European technology, not with the Chinese, and even less with other countries. So this is the challenge we have. And then probably this strategy has to be complemented by the last 2 components, which is an ecosystem for Europe, you can do nothing if you do not create an industrial ecosystem in Europe. We are at the very, very beginning. I think it has been very much highlighted here. We are in the starting phase. We need to make sure that big and smaller industry, SMEs, are again going out there, and therefore we need to see which concrete measures we'll take to promote this ecosystem, and most importantly, to promote the IP, for example, that Mukans is producing today. Imagine that tomorrow a Chinese company comes and says, take 10 billion, he would become a multi-billionaire, but I'm pretty sure that one of our, I would say, Rubins of Europe will disappear. That's essential, therefore, to think what else do we need to put in place, not to be protective, because Europe would always be open, but at least to make sure that our SMEs have the chance to grow up, to scale up, have sufficient investment capabilities, not only from a research perspective, but also from VC perspective, from loans or whatsoever, and market prices, and grow up. And the final dimension is skills, 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 and again, skills. You can forget it if we don't have the skills. It's good that we have today 4,000, 5,000 engineers or researchers, but we need to invest on those skills. And we will come back to that also with a dedicated program. So this is what I would like to paint for the future.
And more women too in this area, yes. Before to conclude, I have one question for each of you. If you have any question to ask to our panelists, so please check your hand, and I give you the microphone. So, yes. Just to introduce you before your question. Thank you.
Yes, thank you. So, Christine Aignan, I'm a member of parliament from this circumscription. And thank you to come here, because usually I have to go to Saclay. I will explain a little bit. First of all, I've been doing physics before, a long time ago. Okay. And currently I belong to several commission of economic affairs, European affairs, and also to the French and German New Assembly. So I had the opportunity last year to do some work on Horizon Europe, the next research program for the European Commission. And also I looked at disruptive innovation. So it was said in your discussion that it's very important for researchers not to work in silo, but to work on more transverse side. I think it's very essential today for innovation. And my question is for you, because you know you belong to DG Connect, and Horizon Europe is DG Research. So how will you also make this connection between all these different directions at European Commission, where sometimes it's difficult to understand how the different programs split and who is responsible for what? My feeling is that we also need some maybe innovation in the way Commission will work.
Innovation, there is plenty as far as there are good ideas on what to innovate. So I have no doubt about that. And don't worry about those things. I mean, it's very, very clear that for us, Horizon Europe is research-oriented and innovation-oriented. So the flagship that we have started in 2018 will continue in principle, thanks, by the way, to your help. So there is an agreement now that not only the quantum flagship, but also the other two flagships that we have in Graphene and the Human Brain Project will continue under Horizon Europe. So in quantum in particular, we hope we will have the funding opportunities in cooperation with the European Parliament and the Council to make sure that the ambitious program that we will put in place will continue. By the way, I take this opportunity to say that today I received the revised strategic research agenda that is our agenda for the next 10 years. So the scientists have been working in the last 5-6 months. So all over Europe, I've been seeing that we have more than 4,000 scientists that have been working on this research agenda. Actually, it's not only scientists, but also industry. And today I just received it 10 minutes before coming here. It is in my table, so I need to have a good opportunity to make sure that this is going out there and is disseminated, and it is disseminated at the political instances in particular. So second, when we want to deploy, to create capabilities, it's not just about research and innovation. So it is really about creating the infrastructures and the capabilities we need for the whole of Europe. So profiting from our investments on research and innovation. This is precisely the idea of positioning activities like deploying the first quantum communications infrastructure all over Europe, or developing the first interactive, I would say, or hybrid quantum computers with classical computers infrastructure in Europe that is available to everybody in the whole Europe via the cloud. So these are capabilities that we'll have to build in the Digital Europe program. So it comes as a total, sort of, I would say, coherence, to use also a quantum expression, to complement what the one program is doing with the other. Yeah? And in the Connecting Europe, then we have the Connecting Europe facility, which is another program, sorry to be a little bit more specific, where all the idea is that we will use this. We will use our traditional computers, where we invest massively, as you know now, right now. This is the Euro-HPC joint undertaking. So we will use this to interconnect everything together and make it accessible for our European users, for our industries, etc., including the quantum. So I give you 3 concrete examples of how we see this happening, and I forgot the skills, but the skills, as you know, in quantum, in computing and AI is part of the Digital Europe program. So all this will come together, and I hope Thierry Breton would have soon the opportunity to announce how all this would be coming together and which are the funds that we will invest.
Thank you, Thomas. Just 2 last questions to you, Albert. First one is about global warming, and the other one is on quantum computers. So on global warming, energy consumption are some of the problems in this world today. Can quantum physics be useful to help this? Your microphone.
Physics in general can be useful. Okay, you know that global warming has become an important problem. And information technology consumes a lot of energy and contribute to this, the explosion of creation, communication, and storage of data. And for example, the information technology in France consume 7% of the production of electricity, which is not negligible. It's more than the planes, according to de Juniac this morning. And for example, we can see that I saw in some papers that a Google's data center in the US consume as the same electricity as the town of San Francisco. And for example, for the public, I can say when you, with 30 searches by Google, you consume the same energy as to boil a liter of water. So it's, you must have this in mind. And so there are solutions to reduce energy consumption by all the computers. Yes, so far the production of a component for computer was simply following the law of Moore. So we knew that every year it was possible to have components smaller, faster, and consuming less energy. But now you know that this law has been flattening off because the heating by a small component is too much. And so we have to think, and this is a concern of the industry, to go beyond this CMOS semiconductor technology. And there are solutions. For example, a turning point has been 2 or 3 years ago, the announcement by several big companies, Samsung, Taiwan, TMC, SMC, of massive production of new components called, not spintronic component, called STT-RAM, spin transfer random access memory, like the RAM you have in your computers, but based on quantum effects, because it's based on the quantum tunneling of electrons in what is called a magnetic tunnel junctions. And so this is a turning point. And for example, Samsung was already this type of component in one of his phones, say that by replacing the first is preparing this component for the next generation of computers and telephones. And Samsung say by replacing in the logic circuits of the processor the SRAM and the flash memory by this type of new component, they reduce energy consumption by a factor of 14. It's not negligible. And the speed also is increased with respect to the flash. And so there are solutions, and this change will progressively penetrate into the technology of computing. And of course, the physicists have other ideas to go beyond even more. And so we know that by exploiting some relativistic effect, like what is called spin-orbit torques, and there will be soon after the STRAM, SOTRAM, less consuming of energy. And also we can use the topological components, this new state of matter that I was talking about. And so we have this concern in mind. When we are working with physicists in this field related to materials and to components, we have always these questions: can we have an idea to low power components?
Two last words to conclude. I know it's two of your favorite topics: quantum computers, bio-inspired computers. Which one will be the most important for the future?
Yeah. So, the quantum computer will be big machine, very useful for some calculation that can be done by usual computers. And neuromorphic computer inspired by the brain are on a different track. So we'll never have a quantum computer in your personal computer, I suppose, and or in your car, but you can have in your personal computer or in your car a neuromorphic computer for all the functions, all the application of artificial intelligences. And today, this neuromorphic computer, like from neurons, have not been in development. So for the moment, if you are, for example, if you look at the neuromorphic computer for IBM with this, what is the name of this computer? Is True North. In fact, a lot of things can be done by emulating the neuron and the synapse to reduce the transfer, because the synapse, the process in the brain is that processing and memory is at the same time by the neuron and the synapse. And so you avoid all the energy transfer between memory and the transistor and logic gates. And so at the moment, a computer like this IBM computer, the synapses are emulated by a microcircuit with 50 or even more transistor. And also I have seen the shape, the size of the neuron. The neuron is also a microcircuit with transistor, which is 100 something very large. And so the idea now is, if we want to really go in this direction, is to find a new type of component to emulate synapse and neuron, not by microcircuits with transistor, but to create a new type of components. So what we are doing in our laboratory in collaboration with Thales. Now what has been begin to be developed also in collaboration with C2N. What has been created is very small components of 1,000 times smaller than the microcircuits, neuron microcircuits of IBM, and also very small component for the synapse. And so this, we are simply on the way. I suppose that in a few years it will be possible to really produce real neuromorphic computers of this type.
Okay, thank you. So we can applaud all these panelists. Thank you. And merci beaucoup pour votre présence. Thank you and good afternoon. Thank you all.